My name is Greg Smith. I'm a professor in the Applied Science Department. My research is in computational biology, not bioinformatics, if you know what that means, as much as mechanistic modeling. So I'm part applied mathematician. I know nonlinear dynamics and stochastic sort of probability modeling, stochastic processes, and the other part of me is a sort of cell biophysicist. So I was trained initially as a biophysicist, and that biophysics means a number of different things, but cellular biophysics is really the study of the electrical properties of cells. So it's a part of biomedical research, cell physiological research, and it's a really interesting field. It's got connections both to physics and also to neuroscience, because the electrical property of cells is really important for the functioning of the brain. So that's what my research is in. And I do have, for anyone who's in the extremes program ultimately, there's projects going on in my lab that involve data analysis. So if you're interested, you can come by and talk to me. This talk is really not about my research at all. I was asked to give a presentation, and the constraint was that it had to be a talk that I'd given recently, because I'm kind of busy right now. And I had given this talk in another context, and so I thought I'd just go for it again. I think it's a pretty interesting topic. It's basically it's a way of thinking about symmetry, and so we're gonna talk about symmetry, several different types, and especially the symmetries of repeating patterns in the plane. So chemists might call these the crystallographic groups, plane groups, space groups. All of the sort of academic acknowledgments should probably go to a group of 3 authors who wrote this book called The Symmetry of Things. John Conway, Heidi Bergiel, and Chaim Goodman-Strauss. It's a great book. It's a little expensive, but it's really beautiful. If anyone's interested, you might try to get Swam to buy a copy or buy one yourself. That's where a lot of the figures are coming from, as well as people online who are talking about this topic, a lot of them making reference to this book. So when you think about symmetry in the plane, the easiest type to describe is what we'll call kaleidoscopic symmetry. So this is when you have lines in the plane, and then the pattern is symmetric with reflection across that line. Right? And you call this little doily pattern here, we would call it star 4. The star right now, you can just think of it as reminding you, that it's kaleidoscopic symmetry. And the 4 indicates that there's 4 lines, 4 mirror lines, right? That the pattern, if the pattern were reflected, it would then sort of congruent with the reflection. And another type of symmetry is gyroscopic symmetry or rotational symmetry. And so this pattern here, we'll just use this little squiggle here, or just use a blue number 6 to indicate that it sort of has 6-fold symmetry. You can rotate it around. The smallest distance that you need to rotate it in order for it to come back onto itself, right, is 1/6 of the full rotation, so it's 6-fold gyroscopic symmetry. And one of the things that's going to happen here in this talk, we're going to build up a little bit of a notation so that you can look at a pattern and just kind of write down, kind of classify what type of symmetry it is. So I'll use this squiggle to represent sort of gyroscopic points, and we'll use a star to represent kaleidoscopic symmetry. There'll be a deeper meaning of the star in a minute. And I think I'm pretty consistent about making gyroscopic symbols blue and the kaleidoscopic ones red. There's one other type of symmetry in the plane. Anyone know?
Inversion? Are you talking about inversion?
Inversion. No, that's not what I'm thinking about, but just the conventional sort of the isometries, or the different types of symmetry you can have in the Euclidean plane. You have mirror symmetries, rotational symmetries, and just one other.
Is it translation?
Yeah, translational, right. Okay, so we're not going to really be talking too much about the translational symmetries, at least not at first. Okay, so the real topic here is going to be the symmetries of repeating patterns. Okay, so a lot of the pictures I'm going to show you are from this book. They're nice. They're pretty. I actually have a sister who's a businesswoman who's an expert seamstress, and one of her companies basically prints fabric, so wholesale. So they actually have computer programs and stuff so that they can design repeating patterns on fabric. I can point you to that type of software if you're interested. But what I want you to do here, right, if we were going to classify this, are you know, in order to find the kaleidoscopic symmetries and to classify it, we need to find all the mirror lines, okay, all of the mirror lines, and then we're going to focus on the smallest element that would kind of be within the mirror lines, and then look at the corners of that smallest element, and that'll give it its name. So, does anyone see any mirror lines here? Yeah.
I mean, in the diagonals of the flower shapes.
Right. Okay. So this diagonal is really prominent, right? And then there's another one coming down like this. There's one going through here. And there's another one going through here. Okay. So if I draw them all in, that's the sort of picture you get. And what you can see is that really the entire pattern is sort of the pigment, right? The pattern here reflected multiple times, right, around the plane. So it was sort of important that this shape that we got here at the end was something that would tile the plane, right, or this wouldn't have worked. And really, in this case, it's this square, right? There's not very many. There's only 3 regular polygons that will tile the plane, right? Triangles, hexagons, and squares. But then if you allow yourself to sort of torque these things a little bit, you get a few other possibilities. So this is really just the square one divided in half here. And to give it a name, to give this type of symmetry in a repeating planar pattern a name, what you'll do is you look at the 3 corners of this smallest repeating element. And this has how many kaleidoscopic lines in this one? 4. This one has 2. And this one has 4. It's important to note that this point and this point truly are different, right? Because the local pattern is different. Okay? And then we would call this star 442 symmetry. Okay? That would be the notation. Okay, so this is the logic behind that name. Pretty easy, right? So let's do this one. So what does this look like? Are there any horizontal or vertical lines of symmetry? Yeah.
There's like 2 separate ones running down the middle of the star thing and the middle of the heart-shaped ones, I guess.
Yeah, okay, the star thing. So there's one like here, right? There's another one here. And then this one is the same as that one, right? So these 2 are actually fundamentally different, because as you move along them, the pattern's different. And then there's this horizontal one, right here, and another one here. Okay, so if we draw all the kaleidoscopic lines, you'll find that the smallest element is this square, right? And it's got 2-fold kaleidoscopic symmetry at each of the corners, so it's star 2, 2, 2, 2. Okay. All right. How about this one? There's no mirror symmetries at all. Okay. It comes a little bit close at times, but there really isn't any mirror symmetry. But there's a lot of gyroscopic symmetry in the pattern. So there's rather than playing what's in my pocket, I'll just point out like what it is, okay? So there's a point right there that has gyroscopic symmetry. Can anyone, how many fold is it? Three. Three-fold gyroscopic symmetry here. There's another point that has three-fold gyroscopic symmetry, and it's different than this one, right? Because the pattern is different locally. And this one looks kind of like this, but it's different, right? It's got the sticks as well as the petals, okay? So those three, I think that's the smallest triangle that you can make. And because there's gyroscopic symmetry at the three corners of this piece that's tiling the plane, it would be called, we would call this 3-3-3 as our classification with no star, okay? 3-3-3. If you want to put a squiggle at the beginning to remind yourself that it's gyroscopic, you could. What about that one? This is your final exam. Go ahead, why don't you touch it, go ahead and stand up and touch it somewhere and tell me what the, if you don't mind.
Yeah.
And you'll get to be immortalized on the camera too.
I think that here would be a 4,
Mm-hmm.
and then here would be a 4 as well.
Okay, so there's 2 4s. Is there anything else?
There's mirror symmetry.
You see a mirror symmetry?
Yeah, going across them.
Going, which way?
Like each flower shape
this?
is like copied.
Oh, yes, so this looks like a copy if you move it translationally, right?
Yeah.
Okay.
Okay.
But there's another way to think about this is that, what did we say? There's this point here, 4-fold gyroscopic. There's this point that's 4-fold gyroscopic, and there's this one here, which is 2-fold. Okay, so this is gyroscopic 4-4-2. Okay, which is sort of analogous to one of the kaleidoscopic ones that we saw. You guys in the back with your laptops open, does that help you?
Yeah.
You searching stuff and
I'm typing on my phone.
cool. Awesome. There's also sort of mixed examples here where it's not all kaleidoscopic and it's all not mirror. So here you have mirror lines that come down here and here, and then there's a gyroscopic point there. So this one would get the name 2 star 2-2. So everything to the right of the star is kaleidoscopic. And this is the smallest element, and that pattern is indeed sort of tiling the entire plane. You can rotate this kind of like that, and then continue doing that on the entire plane. In fact, it's probably best to think of this as do the mirror image first, and then start rotating. Okay, and you'll tile the plane. Okay, so the sort of next level of conceptualization of this is to think about the pattern and the symmetry that you have, and imagine sort of doing an origami type thing where you fold it up, okay, along. And the rule is that the kaleidoscopic, I guess, is the easiest to visualize. If it was a point symmetry and it was kaleidoscopic and it had 4 different lines, right? 1, 2, yeah, okay, 4 different mirror lines. Then you could fold it up and get this little pattern here. And you would refer to the pointy spot as the dihedral corner, right? And the fact that this has the 4 kaleidoscopic lines, it's sort of reflected in this as the angle being pi over 4, right? So it's easy to just take pi over whatever, and that's the same number of lines that you have over here. And then, you know, it's important that when you're folding this thing up, I mean, what's really going on, right, is that pattern R is sort of, if the ink was sort of moving through the paper, it would correspond, to the direction of all the R's that you see in that diagram. Okay, so the folding that you're allowed to do is the folding that keeps the pattern the same as the paper folds up. Now, the kaleidoscopic ones are a little different. It's not really origami because you're cutting, right? But if you cut into the center and then twist paper around, you get a little cone shape. And that's really the topological object that corresponds to the point rotational symmetries. So this is fourfold, and so if you were going to do this pattern, you would be winding around this 4 times. You would take this and you would kind of put it like an ice cream cone here and kind of like roll it around, and you get this pattern back. Does it, I guess this number 4 is also related to, you'd have to think about this a little bit, I guess, but there's some memory of the rotation right here based on the kind of, what would you call it, the solid angle, right, of that cone, right, is going to have a memory of how many times you'd have to rotate it to unfold. Okay, so I'm going to just go through a couple of patterns here and then show you this topological construction that's called the Orbifold for the symmetry pattern. So here, there's the kaleidoscopic lines in this gyroscopic point. And what you can imagine doing is taking this piece of paper and folding it across all the kaleidoscopic lines. And when you were done, you'd get a square, right? Get rectangle. Okay. Since this is being recorded, a rectangle. Okay. And then what? So we've basically gotten this thing that now has no more kaleidoscopic symmetries, right? But then we can sort of cut it into this point and fold it around once and get this shape. So I hope you can imagine doing that. I did actually gave something like this, I mean a simpler level of this talk to middle school students, and I actually had them, they have big pieces of paper that had the patterns, and they had to fold them up and cut them and tape them up to make these shapes. But so can everyone see that this is the topological object that somehow corresponds to the symmetry pattern, right? Okay. It's also becoming clear what this star really means, right? The star is telling us something about the fact that these mirror lines are keeping this object from being topologically a sphere, right? If we somehow if we didn't have any of these mirror lines, right, this thing would be would enclose space, and it would be like a little ball of paper. Okay, but we've had to cut it in order to get these lines here, and that's what the star really means. Okay, so this is the 2 star 2 2, right? I'll show you a couple more orbifolds. This one is 3 star 3 3, and when you fold it up, you get this thing. This is 4 star 2. It's another possibility, and this is its orbifold. This is 2 2 star. There's only one type of kaleidoscopic line, the 2 rotations. This is an example of one that's topologically like a sphere except for the points, right? The 2 2 2 2 gyroscopic symmetry in the plane can be folded up into this object. Now, you're kind of, this one is actually pretty hard to cut and put together into this shape, okay? But it's easy if somebody who's good at this sort of thing has made this shape, you can put it on the pattern and roll it around and see that it really works. Okay? You can roll around these corners, and you would actually see that this one repeating pattern is occurring throughout the plane. Okay, so now there's translational symmetries as well. Okay, and we have to account for those. And we're going to try to think about it topologically, all right? So if you had a pattern that didn't have any kaleidoscopic or gyroscopic points, it could still be repeating, right? That's what I'm sort of doing here with these oysters. Why is it an oyster? That's a long story. Okay. I was trying to make a joke to one of my friends who studies oysters. And he laughed anyway, right? And so there's nothing going on except translation in this direction, and then there's translation in that direction. And it doesn't really matter if I did this or that. But the point is that these two translations are linearly independent, right? So there's actually two different translations that's going on here. In those two different directions, if you think about what is the orbifold, in this case it's a torus. Now you can't really unfold the torus, you can't really roll the torus around the pattern in quite the right way. But what's happening is you've got one direction that's repeating over and over again, and another direction that's repeating over and over again, and that corresponds to going this way around the torus or that way around the torus. So you could really put this oyster pattern on that, painted on one oyster, and it would correspond exactly to what's going on in the plane. There's a couple more. This one where it sort of it flips around. It flips like this in both linearly independent directions. The orbifold in that case is a Klein bottle, so you can either see it or not, but so I won't dwell on that. But that's the Klein bottle. And if you see this mirror line and this mirror line are really different, right? Because this has the opening end of the oyster near it, and this one has the butt end, the joint end of the oyster. Oysters don't have butts. And then you have this thing here, which is the translational symmetry in this one direction. So there's really two cuts, right? And then the pattern is wrapped up like a cylinder. Okay? So this is star-star symmetry, because if this were a sphere, you would have had to cut two holes in it, right? That's what the star-star means. And then this one, star-cross, is the one remaining type, which is one kaleidoscopic line, and then as you move the image flips like this as you move along. So this is basically the one boundary of this Mobius strip. So the way, pretty much that's the full classification, okay, that we've gone through of all the possible symmetry patterns that are in the plane, repeating patterns. It's very different than the issue of how can you tile the plane, right? You can look at some complicated tiling and then try to ask what is the symmetry pattern, and then you have to decide whether or not you consider colors to be important, right? But if you ask all those questions, you'll get an answer that has to do with the repeating pattern, which is different than just what is the shape of tiling the plane, right? If you look at the bricks in a lot of places, kind of look like this. So if you had a brick wall like that, it's pretty clear what's going on in terms of tiling, right? It looks like we're shifting things in these two linearly independent directions. But what's the actual symmetry pattern here, right? We have to find the mirror lines first. And there's a mirror line here. Okay. There's another one here. These are supposed to be on the same spot. And then there's a mirror line here. Is that right? And there's one here. Okay, so this is star 2222 actually. It doesn't have any translation in it, even though it looked like that originally. Okay, so I think I showed you most, maybe not all of them, but most of them. Okay, and this is Conway's Orbifold notation. Okay, Conway came up with the notation, this. So what's going on topologically, right, is that you're starting with the sphere as your base object, okay? And this O means you're putting a handle on the sphere. So if you have, I think maybe a lot of you have seen this, but if you have a sphere and then you put a handle on it like this, right? That's topologically the same as a torus. Okay? So this handle, that's really what this symbol is representing. This was the twofold translational symmetry that resulted in the torus Orbifold. This is the Klein model, twist, twist. This is a cut and a twist, two cuts, puncturing the sphere in two places so you get a cylinder. And then all of these are, you puncture the sphere in one place and then you fold the thing up. Once you puncture a sphere, right, you can stretch it out into a plane. Okay? So this is puncturing the sphere to get a plane, and then this is the kaleidoscopic folding, and so on. So the notation is really beautiful in the sense that it really is capturing the topology of the orbifold, okay, which is corresponding to the repeating pattern. So that's one thing to say. Another is that I believe it was someone named Bill Thurston, a very, very famous geometer, whose work has tightly connected to the proof of the Poincare proof conjecture, right? This idea of using the orbifold to classify geometries was his idea. Conway just kind of came up with a notation that sort of is pretty. Okay, but it was really, Conway became like a prophet for Thurston, basically. It was really Thurston's, ideas about the orbifold. Basically, the orbifold idea is that you understand geometric space groups by the topology of the orbifold. And what's kind of amazing about that is that, we're talking about the topology is what's constraining the geometry. Usually you think of, I guess that's okay, right? Topology is a little bit more general than geometry, right? But you're really talking about this geometric space group, and it's really the topology of the orbifold that's allowing you to, that is what allows you to correctly or logically classify things.
Why 17? Yeah. Why 17?
I watched a talk that John Conway gave on this, and someone said, why 17? And he got visibly kind of like, just like, come on, it's just, it's combinatorics. There just happens to be 17. There's nothing magic about the number. Yeah. So there really isn't, there's really no significance. It's just that it turns out that in our universe in 2 dimensions, this is, what happens, basically. But there is a way that we can figure out that there are only 17, right? Because there's no good answer to why the number 17, but there's a good answer as to why this is all there is, how you can be sure this is all there is, and we'll talk about that next. Okay, so first I'll explain the method, and then we'll talk about why. Okay, so Conway calls this the magic theorem. So you imagine you have $2, okay, and then there's a cost for every one of these symmetries that you would do. Okay? And so basically the handle, putting a handle on the sphere costs $2. That's all you can do. Okay? Poking the sphere with a hole, right, or twisting costs $1. And then the gyroscopic symmetries cost n minus 1 divided by n over dollars. So if you have a symmetry of 2, that's 1/2. If you have 3, that's 2/3. If you have 4, that's 3/4, right? So you're taking the reciprocal of this and subtracting it from 1 to get the cost. And then this one, the kaleidoscopic costs are 1/2 of the gyroscopic cost. Okay. So let's just check this out, right? The gyroscopic 632 is 5/6 plus 2/3 plus 1/2, which is $2, right? The 3*3 is 2/3 for the 3, $1 for the poking the sphere, 1/3 for the kaleidoscopic symmetry, it adds up to 2. Pretty wild, huh? Okay. And if you just think, if you started with this, if you believe this, you could figure out that those 17 are the only possibilities. If you believe that this cost structure. So does anyone have any guesses as to why the number 2 is important?
2 dimensions.
2 dimensions. That's a good thought. It's actually not that though. Is it anyone ever seen the number 2 come up in topology or in graph theory?
Power set?
Hmm?
Power set?
That's not what I mean either. Okay, I'll just, everyone ever hear the Euler characteristic?
Oh,
Yeah.
right, yes.
Okay, so 2 is the Euler characteristic of the sphere, which is the topological object that we started with. Right? So if for anyone who doesn't know what the Euler characteristic is, if you take anything that is the shape of a sphere topologically, like for example, a regular, like the outside of a Platonic solid, right? Is there a name for that? The cube. Okay. And then you calculate this Euler characteristic is the number of vertices minus the number of edges plus the number of faces. Okay, so every dimension you add or subtract as you move up. And the number of vertices here is 8. The number of edges is 12. The number of faces is 6. And I think that that's 2.
Yeah.
And so any shape that's topologically the same as a sphere will result in that number. And you can try this, you can like get a ball or something, right? And then some markers, and then just put dots and draw edges between them. And you have to, you can convince yourself, right, that you know, every time you draw an edge, you're connecting 2 vertices, and you make a change, it doesn't allow this number to change, and so on. All the different operations end up causing the number V and E to go up by 1, or right, or the number E and F to go up by 1. Either way, you can't change the Euler characteristic. Yeah.
So what are these fractions represent?
So the fractions are, see if I can. So it has to do with the change in the Euler characteristic. So if you, let's see, if I had a 2-fold, 2 lines, right, of symmetry, and I let myself fold it up like this, right? Then what I can do is, let's think about this as a thick line, and a thick line here, and a nice little vertex. Okay? Then in this object here, I've got 1/4 of a vertex, right, and 2 1/2 lines. Okay? So that's 1/4 plus 1. In the Euler characteristic world, x is vertices minus edges plus faces. The vertices here was 1. It used to be 1 edge, one vertex, and what did we have? I don't know if I'm going to count this right. 1, 2, 3, 4 edges. Okay. And do I have to think about the number of faces? I don't know. We'll see if this works. And then this became a 1/4 when I folded it up. It's only 1/4 of a vertex now. And so what we're going to do is, I'm going to have to do this a couple times before I get it to work. But you started with 1 vertex, and then you subtracted 1/4 of a vertex, and the cost then, the change was 3/4, and I'm not doing something right because it's supposed to come out to be 3/8. Okay, but maybe that's because we need to keep the edges in as well. So this had, if we called that 4 edges, this only has, this has, okay, I'm going to stop there. So the argument of how you actually prove that magic theorem has to do with thinking about how the folding, right, would give you fractions of faces, edges, and vertices, and then that changes the Euler characteristic.
That actually has
having
maybe
trouble reproducing.
Yeah, maybe have something to do with something I always do. We always do in graph theory is discharging. So,
Discharging?
Yeah, we use this Euler formula and then assign charges to each vertex and each face. And so we come out with fractions. But I don't say how we come out those fractions, but sometimes we do come out different kinds of fractions.
Yeah,
And
so I sat down and worked this out and convinced myself that it worked. Maybe in one of my slides I have it actually presented. Would this one at least work? If you fold something up and fold, if you rotate up, if the only thing you did then is go from one vertex to, like, say, 1/6 of a vertex, then that cost would be 5/6, right? So that one worked, and something else is going on with the kaleidoscopic that I'm forgetting. Okay, so just some more, I guess I'm not gonna give too many more examples, but these are these ones that are a little bit, that we just went through, the ones that were the oysters essentially. Okay. Okay, so now we're going to crank this up just one more level, okay, and we're going to talk about the patterns on spheres. And it turns out that if you think this way, that you can develop a notation for 7 different spherical patterns that are referred to as the parametric patterns, and then there's 7 more that are the platonic spherical patterns. Okay. So the parametric means that there's this number n in there that can be anything. Okay. And what would be an example? The easiest one here is this one. Okay. Here, if you there's kaleidoscopic symmetry line here, right? And but there isn't one here, and there is one here. So there's 2 different types, right? But then there's going to be n of each. Okay, so that's star n. This one is star. There's a kaleidoscopic symmetry here, and a different type here. But these are twofold because the bottom of the sphere is the same as the top, so that's star n2 too. Okay, and the same sort of logic and notation goes through. It's probably not worth it to spend too much class time at this point on those. But it also allows you, if you just look at this piece of the sphere, it allows you to classify what are called the frieze patterns. Okay, so this would be, if you look up in buildings and you look around the edge sometimes, there's these patterns that you'll see. And they're essentially, you know, like you might have, imagine this line here, might have a shape that looks like something that has that type of symmetry. So it's moving in the one direction, but it's flipping each time it moves. And every type is like 7 different ways that can happen, and each one of these corresponds to one of them. The platonic ones are corresponding to the platonic solids, right? So I think each one of these is either a platonic solid, the symmetry of a platonic solid, or some, there's some dual of every solid. So I think if you take all of them and their duals, these are the things that you get. What's the simplest one? So if you looked at, say, a basketball, you could ask yourself, you know, what kind of symmetry does it have? And you know, you have to, or a tennis ball, you know, you have to think about where the seams are, and you can come up with one of these 14 different answers. Okay. Now what's really cool is this seems to be the best way to think about three-dimensional symmetry too. Okay, so at least it's the first time I sort of read something where I was like, oh, it's all coming together, right? So if you're going to have a 3D object and have symmetries, it turns out that there has to be at least one point that didn't move, right? If you're going to reflect or rotate, right, and there's no translation, and there's going to be a symmetry, it has to fix at least one point. Okay, that's a geometric theorem, and you know that's the center of mass or whatever, right? Think of that as the center of mass, and then if you sort of think of that point, and then think of your object and sort of project it out onto a celestial sphere. Okay, so take the image of the object and project it out really far. Then we actually have a pattern on a sphere, right? And then we can ask about the spherical classification of that pattern. Right? So this couch here, when you projected the pattern out, if the pillows are located correctly, right, it's the same pattern on this side as on this side. And if you identify the two places on the sphere, right, that have the same pattern with one another, you get this half hemisphere, right, with the one kaleidoscopic symmetry. So that's like the Orbifold. And so you would, you know, this would just, the symmetry that you might call, in biology, you call it bilateral symmetry when there's one plane symmetry, right? That we would call that star, okay, just star. And there's a memory of how many symmetries this object had in the number. We know that stars cost 1, right? So if you take the cost and then you add, it's the cost of what we do here is always going to be less than 2, okay? And so you'll take the cost and then you'll add 2 divided by something to get this total cost of 2, and that number on the denominator is the number of symmetries in this object. In this case, it's twofold symmetry. So I'll show you a couple examples. So here's a table. It's got, if you project it out onto the celestial sphere, it's got these two different kaleidoscopic lines that are twofold. So we would call the symmetry of that table star 2, 2. Okay? And it's pretty obvious that it's got 4-fold symmetry, I guess, right? That's why the chair has like 4 different legs coming down. But if you took star 2, 2, the star costs 1. What does the 2 cost? It's 1 minus n divided by 2n, right? N minus 1, thanks. So that would be 1 over 4. Is that right? Okay. So this would be plus 1/4 plus 1/4 plus 2 divided by the number of symmetries equals 2. So G is 4. So it's pretty nifty. Here's the symmetries for cube. If you've got, you know, the corners are one place where you can rotate, right? 3-fold. That's this. You've got the edge here can be rotated 2-fold. That's this point, and then the center of the face is also something that can be rotated 4-fold, and that's this point, and that's one of the spherical kaleidoscopic cases. Star 4, 3, 2. And if you do this little calculation to figure out how many symmetries it has, you get 48. And if you actually sort of took this little triangle and then made a little 3-dimensional wedge going into the center of this, you'd see that that's 1/48 of the whole cube. So here's some other realizations of things that have these, what do we call them? Platonic spherical symmetries. This was the argument about how you can work out from the Orbifold notation how many symmetries the object had. And if we go back to what we did originally, right, and we look at one of our planar patterns now, this is 6, 3, 2 star. If you try to figure out the cost, it's the 1 for the star, and then here are the 3 kaleidoscopic costs, and you get 2, right? But that means we're subtracting off 2 divided by infinity, and that's right. There's an infinite number of symmetries because this pattern's repeating infinitely often throughout the plane. So the whole thing sort of comes together. So if anyone's interested, I can share with you, 3 or 4 PDFs of papers that Conway and others have written talking about this. The ones that are describing the Orbifold notation are relatively short and easy to read. Okay. Then there's the book itself is really beautiful if you want to buy it. This is like the first third of the book basically. Starts off pretty easy. By the time the book is done, it is really pretty advanced, right? And that was one of the things that's really nice about this book. It's very interesting to read something that sort of starts off that you can understand it even if you're in elementary school, and then by the time you're done, there's only a couple people in the world who could probably really understand what's going on. What happens to make things complex is that you can do everything in 3 dimensions, right? So here we have these 2-dimensional repeating patterns, and our orbifold was the surface, right? What is the analog of a surface when you're 1 dimension higher? Does anyone know?
Modular form.
Huh?
Modular form.
A modular form. I don't even know what that is. That's a group theory thing?
It's infinite planes of reflection in 3D space.
So what I was going for was manifold, right? So a surface is a place where any locally it looks like the Euclidean plane, but in the global picture it's wrapping and twisting in some manner, right? If you have a space that is locally like Euclidean 3 space, but then as you go far away it wraps and turns around in some manner, that's a manifold. And you can do it in higher dimensions too. So manifolds are really important in theoretical physics because that's warped space-time and all that. And you think about it in terms of all your operators happening on this manifold as opposed to the Cartesian space. So these things that we're calling the orbifolds are kind of like folded up pieces of 3 space that are now manifolds, right? And so it just gets, there's something like 219, I think, different 3D space groups. And Conway's got this paper with Thurston where they're all classified in this way. So if you're interested, a chemist who's interested in math, I mean, this is the right way to think about all of the crystallographic groups. And these papers actually give the historical name of the crystallographic group in addition to the new names that they're coming up with. So that's another thing to say. And then maybe finally, there's a connection between all of this stuff and, in group theory, right? Because if you had, for example, something that had the 3-fold rotational symmetry like that, right? You could think of this not moving it as being the action of doing nothing, and then this is 1 rotation, and this is 2 rotations, but then you have this property that 3 rotations is equal to doing nothing. Okay? So group theory people just do that, and that describes this group. Okay, so there's this action, but if you do it 3 times, it's the identity. And all you need is this rule to make the whole, the multiplication table for this group, which would be 3 by 3. This is called the presentation of the group. And basically, one of the things that is going on that I haven't talked about is that for every one of these symmetries, you can work out the presentation like this by sort of reading through the Orbifold notation. Okay, and every time you see a particular type of symbol, you add another one of these algebraic conditions, right? And I thought that was really remarkable, is that there's this way of, one of the things that makes you feel like this really is the right way to think about things is that you look at that Orbifold notation and you can unpack it, right? And get this group theory sort of description of everything that's going on. So if anyone's interested in group theory, or just, that's another reason maybe to try to get the library to buy this book or to buy a copy yourself, because all of that's in there as well. And that, in the book, that's happening in the higher dimensions as well. Okay, sorry I couldn't work out the kaleidoscopic values, but you guys can, that's your homework. You'll see me again, probably, talking about actual data.